Okay, so last playlist, one of the optional topics to discuss would be why exactly the nth degree Taylor polynomial formula looks the way that it does. And so this is sort of a continuation of some of the videos from last time, but I wanted to talk about that a little bit more. So if we have some function that we're going to call f of x, our goal is to find a polynomial that matches, that mimics the behavior of f of x as closely as possible in the neighborhood of some point. So we're typically going to start off with x equals 0. And so, but when we say that we want it to mimic the behavior, we want it to not only, we want this polynomial function to not only have the same value as our f function at x equals 0, but also the same first derivative, which means that it has the same slope, the same second derivative, meaning that the function's slope changes in a very similar way, third derivative meaning that that changes in a similar way, etc. And if we have more terms if our function's derivatives matches more higher order derivatives of the function f of x, it's going to do a better and better job of matching its actual behavior. So our goal is to come up with some polynomial. So the nth degree polynomial in its general form, so any nth degree Taylor polynomial looks like some constant plus some other constant times x plus some other constant times x squared, etc. And so I'm going to include in the fourth term, because that's the term I want to work with here. But this goes up to xn, cn x to the n. All right, so if this is the nth degree Taylor polynomial, then it goes, the terms go up to an x to the nth term. All right, and our goal is for the various derivatives of this function to match the derivatives of f of x. So if we wanted to find the fourth derivative, so rather than a prime, in theory, you could put 4 primes. You could also put parentheses 4. This means fourth derivative of Pn. Well, this is going to end up being our C0, when we take its derivative, that term's just going to go away. When we take multiple derivatives of C1x, that's going to go away. And that's going to be true for all of our terms up to this C4x to the fourth term. Right. So let's think about what happens when we take this derivative, or this component's derivative 4 times. When we take it once, we're going to get a 4 times x cubed, 4 times c4 x cubed. When we take that derivative again, we're going to get a 4 times 3 times c4x squared. We take the derivative again, we pull this 2 down. And then when we take it again, the x term is sort of x to the 0, so it goes away. And we're just left with 4 times 3 times 2 times 1 times c4. And the point is that we want this evaluated at 0. So if we were to plug in 0, we want this function, or we want this to be equal to the fourth derivative of our function evaluated at 0. In other words, our C4, the fourth term in this polynomial, should be the fourth derivative of f of x evaluated at 0 divided by this 4 times 3 times 2 times 1 part. And you may recognize that this is the factorial. So this is the term that goes in the fourth position in our function here. Right? And this pattern, this pulling down these exponents in subsequent iterations of the power rule, is sort of always going to show up. So the nth term, so the term that goes out here, when we take the nth derivative of this, we're going to get n times n minus 1 times n minus 2, all the way down to 1. So we're going to get an n factorial term. But other than that, we want this to equal the nth derivative of the function that we're mimicking, evaluated at 0. All right. So that's why the general form for the Taylor series, for the Taylor polynomial, looks like this with our factorials on the bottom.